Hi, my name is Ryan Dunn, and I'm a mechanical engineering major from the class of 2019.
And I am Michaela Williams, a biomedical engineering major from the class of 2019.
In this video, we'll be working through problem number 4 from chapter 2 on page 7 in the general chemistry workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you've completed the problem, then we'll go over it together.
Problem 4 states that cerussite is a lead ore historically used as makeup amongst European nobility. It is composed of 77.5% lead, 4.5% carbon, and 18.0% oxygen. Cerussite has a molecular weight of 267.21 grams per mole.
Part A asks us to calculate the empirical formula of cerussite. An empirical formula of a chemical compound is the simplest positive integer ratio of atoms present in a compound. To start, we are going to use the composition of cerussite to solve for the molecular weight of each element. We are going to find the molecular weight of each element by multiplying the molecular weight of cerussite by the percent composition of each element, lead, carbon, and oxygen. So for lead, we multiply 0.775, which is the percent composition of lead in cerussite, by 267.21 grams per mole to get 207.08775 grams per mole of lead in cerussite. For carbon, we multiply 0.045 by 267.21 grams per mole to get 12.02445 grams per mole of carbon. And then for oxygen, we multiply 0.18 by 267.21 grams per mole to get 48.0978 grams per mole of oxygen. Now that we have the molecular weight that each element contributes to cerussite, we can find the number of atoms each element contributes. To find the number of atoms each element contributes, we will divide the weight of each element by its atomic mass. The atomic mass of each element is found in the periodic table underneath the element atomic symbol. For lead, we take its molecular weight from the previous calculation, 207.088 grams per mole, and divide it by 207.2 grams per mole, which is the atomic mass of lead from the periodic table, which gives us 0.999 atoms of lead, which we round up to 1. For carbon, we do 12.024 grams per mole divided by 12.01 grams per mole. Again, the atomic mass of carbon from the periodic table, which yields 1.00 atoms of carbon. Again, we rounded to 1 from the non-integer value. Lastly, for oxygen, we divide 48.099 grams per mole by 16.00 grams per mole to get 3.00 atoms of oxygen. Now that we have the amount of atoms for each element, we can create a molecular formula. To do this, we put all the atomic symbols together, and the number of atoms of the element is the subscript of that symbol. So we end up getting PB1C1O3. And since 1 is the smallest positive integer, our formula is at the smallest positive integer ratio, which is the definition of the empirical formula, as mentioned earlier. Additionally, the subscript 1s don't need to be written, since it's assumed you have one atom of the element when it appears in the empirical formula. So PbCO3 is the answer for part A. Part B asks us to determine another name for cerussite using the empirical formula determined in part A. To do this, we must be able to determine if a molecule is ionic or covalently bonded, and we also need to know how to name ionic and covalent molecules. Starting off, we need to determine if this molecule is ionic or covalent. Recall that covalent bonding occurs between two nonmetal atoms. Ionic bonds, meanwhile, occur between a metal and a nonmetal. Since the molecular formula for cerussite from part A is PbCO3, we know that Pb is a metal and the CO3 compound is a polyatomic compound, which is not a metal. Therefore, we know PbCO3 is an ionic compound. Something important to note is that while CO3 is covalently bonded between the carbon and oxygens, the CO3 compound itself is bonded ionically with lead. Proceeding to ionic nomenclature, the naming rules are quite simple for ionic bonding. It goes name of cation plus the name of the anion. The cation, which is the metal, retains its full element name. So Pb, the first part of PbCO3, is named lead. The anion, which is the nonmetal, has two outcomes. If the anion is not a polyatomic ion, it becomes the anion name appended with IDE. For example, fluorine becomes fluoride. If the anion is a polyatomic ion, as it is in this case, the naming for the anion is simply the name of the polyatomic ion. So, as you should have memorized, CO3 is named carbonate. Pulling it all together, the overall name of PbCO3 is lead carbonate. The last thing to determine is the charge of lead in the lead carbonate compound. This part of the naming convention arises from the fact that lead can have multiple electron configurations, leading to ionic compounds that have names that appear identical but have different configurations. An example, CuCl versus CuCl2. Both of these, using the naming convention outlined a minute ago, have the name copper chloride. However, they're clearly different, and in chemistry, every compound must have a unique name. Thus, we need to introduce a second identifying factor to distinguish CuCl from CuCl2. We do this using the charge of Cu. Recall that chlorine has a charge of -1. So for CuCl to be a neutrally charged compound, Cu must have a charge of +1, while for CuCl2, Cu must have a charge of +2. So using the copper charges, we have CuCl is named copper 1 chloride, and CuCl2 is named copper 2 chloride, which again is based upon the charge of the copper ion. Returning to PbCO3, CO3 has a charge of -2, so Pb has to have a charge of +2 to remain a neutrally charged compound. Transfer that to the name of PbCO3 from earlier, lead carbonate, we now have lead 2 carbonate. And we're done.
To recap what happened in this video, we solved for the empirical formula of cerussite in Part A, and then in Part B determined another name for cerussite by following ionic compound naming rules.